What's up, guys? Yeah, so welcome to my algebraic geometry. Lecture. Hope you guys subscribe to my channel. Yeah, so previously I talking about definition of sheaf, and I think the problem, the fundamental topic in algebraic geometry is that you really need to understand the detail of sheaves and the pre-sheaf or something that so that you can try to keep going. So if you follow Harson or Veckel, that you need to understand the sheaf morphisms. So I think this is all the fundamental that I'm not going to prove something, but I want to highlight everything. Okay, so previously I already introduced a ring space given topological space, and you have always sheaf on ring on X. This is called a ring space. Okay, and basically, simply speaking, that given open set, you get a ring, right? So it's a ring space and satisfies sheaf axiom. Okay, so today I want to talk about more about sheaf. Okay, so keep going. Let me just introduce this. I usually think this is very hard, right? So let's introduce this VX OX module. Okay, so I speak this as O, right? But okay, so the idea is that somebody give you a ring space, and we can define, let's say F is a sheaf of abelian groups on X. So sheaf of abelian groups on X, and then we say okay, so we can say that F is a OS module. Okay, I should write this. OS module means that for every open set belongs to, so this is open set of X, then F of U has a structure, structure of OS module. Sorry for sometimes my OS always looks different. Okay, but basic idea is that right, so the definition of module is very obvious, right? So basically, given an abelian group, if a ring can act on abelian groups, then you can define module, right? So if for each F of U is a structure of OS module, and this is not enough, right? So we need some compatibility equations, right? So for example, let's say V belongs to a subset of U, right? You have a restriction map, right? So you have an OXU, which is a ring, times F of U, will go to F of U, right? This is the ring, act on abelian group, go to abelian group, need to satisfy the restriction map. Okay, so you can get this diagram must commute. Okay, and then for this one, you just get RU new and crossing with RU, right? So this is this is just two restriction, and then there's a particular restriction working on a sheaf of F, right? So I think this is very natural. Okay, so up to here that we not just have the ring space, we also have the module, right? So basically the sheaf of modules. Oh, so this is very, very important, right? So we have a sheaf of modules. So you once you have this idea, then you can talk about more difficult things. Okay, so a very simple idea that notice that the stocks of FP also become a VX module. Sorry, I should say OS module. OS module. Okay, so example that is very famous is the vector space. Okay, so sorry, the vector bundle. Okay, so you can check that this. If you have vector bundle, then you can check that this is a OS module. Okay, and okay, so you just check, and then give a definition called a sheaf of morphisms. Okay, so let's say give F of G is a sheaf on X. Okay, with the value in some categories. Okay, so I think this should be used abelian categories, right? So rings, abelian groups module. Okay, so most of the time we always work on these three objects, right? And then let's say phi is this phi is from F to G is a morphism. When I say phi is F of G is a morphism, means that if it's natural transformation. So remember the pre-sheaf or sheaf, the definition must be a functor, right? So it's a morphism, natural transformation between F and G. So means that for every U belongs to open set of X, that you have phi of U map to FU, right? So FU is a sheaf of abelian groups or something, map to GOU, such that for every V is a subset of U, you have the compatibility of restriction. Okay, so hope you guys can understand this equation, right? So something I hope you guys can understand this equation, right? But because phi of u makes to this, then you can do a restriction, right? So you can check that this is just very simple. Okay. Okay, so now we can talk about, so once we have this morphism, we can describe a category of pre-sheaf, right? So we can category of pre-sheaf, say with value in C. Categories. Okay, so basically this is a category of pre-sheaf, right? So basically you can ask that you can given a topological X, topological space X, then you can define you can create a category of pre-sheaf, right? So basically the objects is the sheaf on X, and the morphism, sorry, this is objects, and the morphism will be the sheaf morphisms. This is an important idea, right? Because in the future, one want to define a so-called, one want to define a locally free sheaf or the coherent sheaf, quasi-coherent sheaf, need to say something called a sheaf morphisms. Okay. Okay. So let's do some example. Okay, so this example, I think it's not so basically if you have two vector bundles, let's say you have V to V prime to X, and you can vector bundles, right? This is, so each F, this kind of F is called bundle map. If you check the bundle map definition, then you can see that F is just a sheaf morphisms. If you check the bundle map definition. Right, so the vector bundle is actually some particular case of the sheaf called the locally free sheaf, and I will describe in the later. Okay. Okay. So now let me just give some notation. So I use a set of X, means that the sheaf of the category of sheaf of set, and also ABX, or basically module X, basically the sheaf of this category of sheaf, but with the module structure on the ring space. So our OX, this is our setting as a ring space and always a structure sheaf. And I can define these three kind of things. Okay. And also, obviously that if you have any phi from F to G leads to a morphism between sheaf, then you can take it stocks, right? So you can there will be some induced map from sheaf. Okay. Okay. And also you can also use the push forward, right? So basically, yeah, I mean you can check this. Right? Okay. So now once you have sheaf, then somebody give you two sheaf, right? You can define all the natural transformation as a set, right? So this is a definition called home sheaf or sheaf home. So idea is that somebody gives G, let's say two sheaf of X set, let's say two sheaf set, and then you can define a pre-sheaf, right? You can define a pre-sheaf of sets. Basically, for any U belongs to open set of X, then you can define a hum of, let's say, F and G. Basically, this is all the natural transformation or all the homomorphism. Phi restricted from F restricted to U, mapped to G restricted to U, and the phi is a morphism of sheaf. Okay, so this is very non-trivial. That you can check that this is well defined. Okay, they are by definition are well defined. Okay, and you can check that I think if F and G are both sheaf, then you can check that it's hum. This is non-trivial exercise, or so you can just Google. It will be a sheaf. And so basically, you take any abelian, maybe sheaf of abelian groups, and you can define a home of abelian groups and the home of rings and the whole of all its modules. Okay, so let's say abelian groups and the ring or modules are similar. Okay, so basically, given any two sheaf, then you can define a home sheaf. Okay. Okay, so I usually want this lecture like somehow like the introduction. So basically, I talking about some fact that, but I don't give the proof. You can see the hard zone that somebody give proof. Proof is very non-trivial in algebraic geometry. Okay, so let me just leave another definition. So if your phi is always module, I should say always module sheaf, and then you can define a hum of f of x. Right, so this is a sheaf is always is also a sheaf, right? So basically, always become a structure rings local ring space is a structure sheaf originally become identity module, right? So you can take the hum of this module vx ox. So these guys are called a dual sheaf. Okay, it's called a dual is a sheaf of f. Okay, so this is the generalization of the dual, like a vector space, right? Because you can view the vector bundle, right? So if your space is flat, then this guy becomes just the dual of the vector space. Okay, so once we have this sheaf type of morphism of sheaves, then we can define similar things like kernel, cokernel, so many trouble. Okay. Okay, so now I can define. So somebody give you f and g, right? Becomes abelian groups of sheaves. Then let's say you take these, then you can define a kernel. Okay, cokernel and the cokernel. Okay, so for every open set belongs to T of X, then you can define a kernel. The kernel is a sheaf on U. Basically, it's a kernel of V of U from F of U go to G of U. Right, because this is so given any sheaf, you can define another kernel. Like morphism, give you a morphism of two sheaf, you can define a kernel. Okay, so you can define a cokernel. It's basically the cokernel of this map. Okay, so amazing things happen theorem. So kernel is a sheaf. Okay, so you need to prove the sheaf axiom, right? So this is you can view as exercise or basically see Harshal. I think this is a simple exercise that you can go to check. I think this is not very trivial. This is not difficult. Because the kernel will take. I mean, if you go to a sheaf axiom, I think the kernel is obviously that it will work out, right? But cokernel is not a sheaf. It's not a sheaf. I think most of some fact in the algebraic geometry comes from this fact that cokernel is not a sheaf. Okay, so let me just spend time and describe why cokernel is not a sheaf. And I think once we done this, then I can talk a little bit about the sheafification, and that would be that would be enough. Okay. Okay. So explain. So let me just explain why cokernel is not a sheaf. It's not a sheaf in general. Okay, so this lies a fact that in the complex analysis. So let me just quickly say it. Okay, so there's no global function from complex number to complex number such that f is holomorphic and holomorphic, and the exponential f will be z. Okay, so these yeah, right. So this is just saying that there's no global log function. I think this is a simple complex analysis that I think you guys already learned it, right? But because if you close, for example, if you define let's say you may say, oh, f just defined with log z, right? But if you write it as a complex coordinates, you can make log z plus I theta, right? But then now will be a branch cut, right? So you cannot cross this, right? So it's not always defined. It's not holomorphic on this line if you choose branch cut to leads. If you choose another branch cut, you still cannot get a whole complex line, right? So this is just a very simple complex analysis fact. Okay, so let me just create the counterexample. Okay, so idea is that you can define, let's say you take the complex plane and then you take the OS module. You take this OS module to be the holomorphic sheaf of holomorphic function, right? So this is the sheaf of holomorphic function. Okay, so obviously that this is a sheaf. You can easily prove. And you can define another sheaf, K, another pre-sheaf. It's called K of U. Basically, somebody give you open set on complex plane, and you map to 2 pi I z. Okay, so this is a local constant sheaf. Okay, so basically, for each U, right, you just map into 2 pi I z, and for each for everyone looks 2 I z. Okay, and your morphism phi just to be K to be the set of C. Okay, so you need to do the simple you can just do the simple inclusion, right? Right, basically, yeah, so you can just do the simple inclusion, right? So this function is trivial. This function just map this to be 2 pi z, map to some integer. So you can just do the inclusion, right? And then you can check this is a morphism. And you can define a cokernel, right? You just you can check it just a complex number, right? Okay, so basically, this is a famous short Z sequence such that you get to K and O of C, and then go to C, which is a complex number, goes to 0, right? And then the map just right, this is a map phi, right? This is a kernel, right? This is the surjective map. Okay, so basically you can prove. Oh, I didn't explain what is the exact sequence of the sheaf, right? But basically you take each open sets, then it becomes sheaf. It becomes exact sequence. Okay, so let me just explain why, right? So the reason is, so now why cokernel is not sheaf. This is a very elementary way, right? So basically you can take, let's say like you want to be the complex plane mod the x greater equal to 0, and the u to be complex plane mod x less or equal to 0. Okay, so you can check that you can. So now I kill it, right? I kill it. So that means I kill it, right? So there is a global lock, right? So there is a function f1, right? There is a function f1 such that exponential f1 is z, okay? And there is a function f2, exponential f2 on z, right? So f1 lives on u1, and f2 lives on u2, okay? Right, so you can take these two functions, exponential f1 equal to z, I mean locally on this u1, and so globally on this u1, and f2 goes to z, right? But I know what? I know that there's no global function, right? There's no global function f such that z it goes to exponential f, right? So from this map, that I tell that I know what? I know that z, right? I know that z is not this z functions is non-zero, right? Because this cokernel means that it in a cokernel world, makes it basically just the idiom right? So basically just this guy modulo this guy, right? So if there's a global function f such as exponential function f is equal to z, that means that z is 0 in the cokernel. Okay, so z is non-zero in the cokernel. But what? But f1, f2 are 0 in cokernel. Zeros in the cokernel, right? Because they are well defined, right? So by the Sheaf axiom, if there is a function which there is a Sheaf axiom. So let me require that we just recall Sheaf axiom. Right. So one Sheaf axiom is that let's say your U is covered by this UI, and then suppose you can find suppose that you get a function. Suppose you have two functions f and g, such that f require restrict on UI is all the same with restrict on g, then f should equals to g on u. Right, this is a Sheaf axiom. So now f1 and f2 are zeros, right? Are zeros in both u1 and u2. and zero restricted on, so zero restricting on these two should also be zero, right? But z is non-zero, right? So basically, this is a contradiction. If we assume cokernel is a sheaf, right? Because the zero restricting on U1 and U2 are zero, right? But the z is non-zero, right? So it violates this problem, this condition if you view f is z, right, and the g is zero, right? So they both restricted at zero, right? Zero restricted at zero, z restricted at zero, right? But there's no such f, right? So this z is non-zero. Okay, so this is not happen, right? So z is non-zero, but zero is on u. Okay, so this is a very elementary idea that this is a sheaf. Okay. So what? Okay. So we need a stupid. We need a very strange technique called the sheafification. I think this is the thing that how to spell, right? So basically, the idea is that somebody gives you a pre-sheaf that you can construct another sheaf, f tilde, which is a sheaf. Right, so this guy is a pre-sheaf. Okay, so this construction is very weird, and to be honest, it's very hard to. I don't want to describe in the video, right? but you can go to check out. Okay, so basically, in sometimes that somebody defines something in the sheaf, if it's not somebody give you a sheaf and you manipulate something, if it's not pre-sheaf, then finally, if the result is not sheaf, then you can just do a sheafification, right? So this is the strange part that I think is very unnatural. That actually there is a way that you can pull out something bad and add something good, which make a pre-sheaf become a sheaf. Okay, so yeah, I think that's enough for today. And yeah, this actually I need, and then we can describe like the how to glue in the sheaf and define something like pull back and yeah, I think and then we can define a coherent sheaf and a quasi-coherent. Yeah, I think that there are a lot of details, right? And but basically, I think these are most important one. Then we can introduce the skins. We'll see you guys in the next videos.